Hey guys, my name's Frank, and this is my workshop. Welcome to part 2 of the Cub Cadet mini motor grader build. In part 1 we covered the disassembly of the original 2 donor tractors and how those components were reassembled to build the drive line for the grader, how the engine was mounted, the drive method, seat, fabricating the main frame which links the drive line to the front tires, front wheels, power steering, and how the overall tractor was built and assembled. At the end of part 1 we were getting close to fabricating the traction frame. We had selected the blade or mold board, and at that point we had to make decisions about how the traction frame was going to be set up and how it was going to work. So that's where this video picks up. Building the traction frame, all the hydraulic cylinder attachment points, decisions that had to be made there, and so here we'll pick up with the traction frame being assembled on the workbench, being tacked together in preparation for completion. Here's the traction frame on the bench. I've made the miter cuts in the, this is 2x4 rectangular tubing again. This is 1/8 inch wall. You see I have a hitch coupling on one end, and here it's placed in the frame, the main frame, coupled to the ball at the front axle assembly and attached to the mold board at this point. So here I'm looking at the length of the traction frame in terms of its placement fore and aft. Since it's bolted to the coupling, that can be adjusted. I could cut it if I needed to, and also to make sure that it looked right and sat in the proper position underneath the main frame. Alright, I'm beginning to fabricate the components that support and hold the hydraulic cylinders that manage the traction frame and mold board. So here are a couple cutouts from the steel tubing, which wind up being brackets for the vertical cylinders. I've put the mold board on a moving dolly so that I can move it back and forth and assess the range of motion necessary for operation of the mold board. Here are some brackets which I've the ones you just saw me cut out in the previous picture, and some smaller ones on the traction frame, getting ready to mount the hydraulic cylinders. So I'm working out the geometry for the cylinders, the length of stroke necessary, and once I figured that out, where my attachment points are, I started to fabricate all of the attachment points. So there are upper and lower attachment points for 3 different cylinders, so it's a total of 6 different. There's a couple extra in that picture. Here you can see the first of the hydraulic cylinders mounted. The brackets are still clamped in place just to make sure everything is going to fit. And at this point, working out the geometry for the attachments. Here, the collars which go around the vertical cylinders, hydraulic cylinders, I'm fabricating them. I've had to machine rings and stub shafts welded to the rings to support the cylinders, so those support the cylinders at those brackets on the main frame. Working out the geometry was a little complex and took some time, and making sure that the connection points didn't bind. At this point, you can see the ring here that supports the vertical hydraulic cylinders. I realized that each of the connection points needed 3 degrees of freedom. That is, they need to rotate in all 3 axes in order to avoid any binding. So my solution to that was to build trunnion bearings. So here I've machined discs out of, I think this is 4140, and purchased thrust bearings from McMaster, and the thrust bearing goes into the housing here. The thrust bearing separates the 2 halves of the trunnion bearing here. The fit between the 2 halves is very close, and these are packed with grease. There's not a lot of movement in these trunnion bearings. It's only a few degrees, 5 or 10 degrees back and forth. It just needs to carry the load, and so the key point here was they needed to be strong. So one of these halves of these discs is welded to the frame, and the other half rotates with the hydraulic cylinder. Each of the other attachment points to the traction frame had to have the ability to rotate as well. So here a series of washers and thrust bearings are used with some nylock nuts, and this is an attachment point for one of the Slew cylinder. And here's another picture of it. So this is bolted to the traction frame with thrust bearings on both sides. So this rotates easily in the traction frame and can handle the motion. You'll see the trunnion bearings now attached to the frame, working out the placement to make sure that everything aligns. Those brackets to support the cylinders had to be cut, and you see they're bolted together in order to get the collars in there. And once I was satisfied they were in the proper location, I tested out the motion, removed the caps from the cylinders, and was able to operate the cylinders even though they weren't attached to the hydraulics. The trunnions are welded to the main frame. Here I'm fitting the Slew cylinder support, which is a piece of 2x4 steel tubing. It's mitered at the far end with a plate that's horizontal welded to it, and then at the near side against the frame there's another plate that's welded to the end of it, and it's mitered at an angle. And here that angle and the length of that support arm are important in determining the range of motion of the traction frame right and left. And so here I've got a piece of wood. I'm kind of looking at the angle and trying to decide the length of the hydraulic cylinder that would make sense here. So I was buying stuff as I needed it, and often would build something and then wait a week or something for parts to come, because I didn't want to order parts that wouldn't fit. Even though I did wind up with a couple of extra hydraulic cylinders that just didn't look the same in the catalog as they did when they arrived at the house. So here's the Slew cylinder being fitted to the test fitted to the frame, checking it for its operation and deciding on where to put that connection point at the right end, which is drilled through the traction frame several inches in from the end. Here's just another view of the Slew cylinder with the support arm clamped to the main frame. And again, as I mentioned, as I go along, I'm painting parts to prevent rust, and also to lend some some realism to the appearance. So, all of the construction decisions are made on the fly based on what things look like, and so having the proper yellow color helps make it look like it's supposed to look. All right, so the next thing I need to attack is the hydraulics, and I purchased 2 twin spool center detent valves to operate the cylinders. I needed 3 spools for the traction frame, so I bought a total of 4 valves, which would give me the upper hydraulic cylinders right and left, and the Slew cylinder with a spare one for the blade rotation, which was a later implementation. So I've run the hydraulic lines to the cylinders here. Everything's been painted. You can see the pin sticking through the blade circle there, and getting ready to bleed the hydraulics and test them out. So here you can see the lines run to the spool valves and to the Slew cylinder and the 2 lift cylinders. Most of my hydraulic components were purchased from either surpluscenter.com or Northern Tool. Some cylinders came from one or the other, and the parts, connections, and stuff came from one or the other. The hoses I had made up at the local Napa. So at this point, I had a working machine. I had to pull the pin to rotate the blade, lift the blade, rotate it manually, put the pin back in, but it was fully functional in as far as pushing dirt around. I don't have the wheel weights on the rear wheels in this picture. I only have them on the front wheels, but it is a largely functional tractor at this point. And I believe that the first video on my channel, the one that has over 500,000 views, is of the tractor in this configuration. Here you can see the blade circle with the pin, which is pulled to rotate the blade and lock it back in position. The castle nut there holds the top of the moldboard post. Again, here's another picture of the blade circle and the traction frame, how it's attached to the moldboard support assembly. So here's just another view driving down the road. It's what it looks like from the operator's seat. I'm testing out the tractor's function. It's a little bit complicated. You feel like you need to be an octopus to operate all the controls at the same time, but it's a lot of fun. Here's a drive belt attached to the front PTO of the engine. So in this first implementation, you'll see this is a single drive belt. There is an arm which actuates that clutch, so you can disengage the belt in order to start the engine. Here I'm back at the mill, milling a clamp sleeve out of a piece of, I think it's 2-inch diameter stock, in order to be able to attach to one of the shafts to actuate the speed control lever with the foot control. So that clamp sleeve is on the inside of the large rod which supports this foot pedal arrangement. So this allows the tractor forward and aft motion to be controlled with your right foot. Okay, second phase of the build was installing the hydraulically driven blade circle. So here you'll see the gear, which is a ring gear out of an 8.3 Cummins, welded to a 1/2-inch disc that I had water jetted locally at a fab shop. I welded the ring gear to the disc, and here I'm mounting a hydraulic motor. I had to make some changes to the traction frame support brackets, so you can see the pin disc is welded now in place to the traction frame, and fabricated a support for the hydraulic motor. Had to bore out the pinion gear to fit it to the motor shaft, but that wasn't a major task. So here the motor bracket is bolted to the frame. The only critical thing here is gear mesh between the pinion on the bottom of the hydraulic motor and the blade circle gear. And the blade circle is not intended to take, the gears are not intended to take the load of the blade. So there's actually a locking pin which was also installed. And it's visible in one of the other videos on my channel. Here I'm updating the drive to a double belt arrangement, which requires a tensioner to detension the belt so the engine can be started. The starter motor just doesn't have the guts to turn over both of the transmissions during the starting sequence. So you need to decouple the engine from the transmissions to allow it to start. So you can see the double pulleys down on the modified drive shaft, which connects the two hydrostats together, and then the double pulleys there on the engine. Here you can see the belt tensioner and how it tensions the belts. In this picture there's a bolt there on the left which is used to tension the belt, but a later update changed that over to just a little lever which is flipped to tension and detension the belt. And there's a video on my channel showing that the fabrication of that lever and how that works to replace this bolt method to tension the belt. In the interest of full disclosure, I just wanted to share an effort here which I ultimately abandoned as far as a drive method for the grader. I was concerned about the single belt from the very beginning. The single belt failure leaves the tractor stranded. It's difficult to tow, it's unmanageable, so I was concerned about reliability. I did ultimately decide on the double belt drive, which does provide some redundancy, but while I was thinking about that, I went down the path of hydraulic drive. Not the most efficient way to do it, but I felt that it would be much more reliable and basically maintenance free. So a pair of hydraulic pump motors. Here's the pump attached to the rear of the engine through a flex coupling, and you see the relief valve there. This draws hydraulic fluid from the 8-quart reservoir in the rear axle. So had to modify the rear axle cover with a dip tube and a return and a pressure relief and that sort of thing. So that reservoir has its own filter and is a sizable heat sink. So there's no other additional dedicated cooler, though I did look at that and felt like it might be needed depending on heat load. Here is the actual hydraulic motor, which is mounted behind the rear hydrostat and drives the hydrostat from its rear input shaft. And you can see the connections to the reservoir there with caps on them right beside the connecting shaft between the motor and the hydrostat. The hydrostat is that finned aluminum object there in the middle. So I did get this working. It heated the fluid up pretty quickly, and Again, not every solution you come up with solves all the problems, and in this case, I felt like the loss of efficiency was going to be a pretty big price to pay, with maybe 80% efficiency in the pump and then 80% or 85% in the motor. I'm down to 60% efficiency, losing a good bit of horsepower. So that got me rethinking the belt drive situation, and once I was able to come up with a way to tension the belt within the frame, and there's not much space to tension the belts, to build a tensioner, and I worked on that and figured I could do it. So I wound up disconnecting all of this hydraulic arrangement here and abandoning the whole idea of the hydraulic drive. The point of sharing this is just to show that not every path you go down in fabrication comes to fruition. Things you think might make sense don't pan out, and there were a lot of little things that I fabricated and they didn't fit right and had to redo, and that's a lot of that has to do with the ad hoc fabrication method that I tend to use. I don't have written plans or don't have plans for this tractor, so everything was pretty much seat of the pants and design and build as you go. I'm kind of a visual guy, so seeing something helps me make decisions, and I think it worked out reasonably well. I did some research, and here's a picture of a motor grader, and you can see that to some extent the frame shape and scale, the length, the wheelbase, the size of the frame relative to the tires, all of that stuff went into the decisions I made about the blade. Where is the blade located between the front wheel and the rear wheels? Where is the operator position relative to the rear wheels? Where is the blade relative to the frame itself, the main frame? How long is the traction frame? All of those kinds of decisions were scaled off of photographs or drawings such as this that I found online. And I think if there's one thing that helps in the overall appearance is to have it be scale, have the design look like a scale model. Not exactly, but close. And I think that really helps. I had a lot of people suggest that I put a cab on it. That, unfortunately, a cab big enough to sit in would be out of scale. And so it would throw off the whole scale and make it look, I think it would make it look lopsided and just, and cumbersome. So having, pictures of motor graders to look at, helped make, a lot of the design decisions. Things that I did not do that are often found on real motor graders include slewing the wheels, and you can see here in this picture the wheels are tilted to one side. A lot of the graders are also articulated to reduce their turning radius. Neither of those were things that I was willing to go down the path to do. It would be just way complicated. I had people comment on some of the earlier videos that I should turn my front tires around. They should face the other way. And here in this picture you can see they face the same way as the rear tires on this particular grader. So the ag tires are directional. So normally the rear tires and face this way. Some people suggested that the front tires should face the other way. So I have my grader arranged with the tires just like the one in this picture, this galleon in this picture. So I do have to give credit to a gentleman who had what I consider an even nicer Cub Cadet motor grader that I saw pictures of on the internet and at a tractor show. So seeing pictures of his were really part of the inspiration that got me thinking about doing this. So his, I think, was even more realistic than mine, though it was built on an older model Cub Cadet frame, and was, as fully functional as this one. So I've got to give, kudos to that guy. In this particular shot here, I don't have the rear wheel weights on the rear tires, and of course this does not have the functioning blade circle. It still has the pull the pin and rotate the blade and reinstall the pin. So this is just a walk around of I would say the first implementation, the first functioning version of the tractor. So the up and down controls for the blade are on the right, those two black handles. The outside handle here is the slew, so I'm operating the slew right and left with that handle. The inside handle on the left is ultimately used for the hydraulic motor for the blade circle. So at the point that this video was taken, the gear-driven hydraulic blade circle was not implemented at this point. So you can see the blade being raised up and down with the lift cylinders, and actually this blade still says Land Pride on it. That gets replaced with a Cub Cadet decal later on. One of the frequent questions on some of the other videos on my channel were about, how long did it take to build, how much did it cost, can you send me plans, that sort of thing. And many of the comments were very complimentary, and I was just really astounded at the kindness of so many of the comments and all the guys that made some really, really funny compliments. So I appreciate all of that. I spent about 3 months working on this from start to finish. It was at the beginning of right before the pandemic hit in the beginning of 2020. I started in February. I finished up in April. I probably spent, 200 hours maybe working on it. Sometimes I'd work all day. I am retired, so I have the luxury of being able to work on whatever I want to work on. So there were some days I spent most of the day in the shop. Other times I'd go out after dinner, work for an hour or two. So it varied. How much did it cost? I didn't keep track of all the expenditures, but I do know that I spent over $1,000 on hydraulic hoses alone at Napa. I'm guessing if you count the two tractors, which cost $400 and $250, so $650, and the cost to rebuild the engine, which was probably $300, and the blade was about $300 when I had to replace the one I stole off my Kubota. Tires were $100 a piece, and $400 or $500 in steel, and $1,000 in hydraulic fittings and valves and cylinders. And I'm thinking the total cost was somewhere between $6,000, maybe $7,000. So not outrageous for the machine that it is, but it is a sizable investment. I mean, I think I paid $250 for the power steering components and the wheel spindles and that sort of thing. So anyway, that gives you an idea of what it took in terms of time and cost. So I hope you enjoyed this recap of the construction. Sorry I didn't have live video, but maybe this is a close second to that. I do want to thank all the folks that commented on the previous videos and watched them. As you can tell, I'm pretty new to this whole YouTube thing, but I do appreciate all the comments. I try to answer as many as I can, and everybody's comments have been super supportive and very kind, and I really appreciate that. So maybe this gives somebody some incentive to go out and try to do something similar, do something even neater than this. I hope it does. And doing something like this can be very satisfying. So I hope I was able to provide enough information to let you decide if this is something you might want to try. So good luck with that. See you soon.